Okay, so welcome to the sixth week in this course on Introduction to Machine Learning. Today's today's lecture would be on neural networks. So I went through the lecture slides which have been presented to which you must have gone through in the course. So I will talk about neural networks and the algorithm that is used to train neural networks. Till date, it is the only algorithm that is used to train neural networks. That is the backpropagation algorithm. I will not derive the backpropagation algorithm because that is there in almost all lecture slides, and I think that has been done by Mainak yesterday as well. So which is why I thought that maybe I will talk about how to go about computation graphs. And so my lecture would mostly be based on the concept of computation graphs and how they play a role in order to give you the backpropagation algorithm. So that will be the agenda for today. So let's start. So as always, if you have any questions in between, you can stop me and ask. Okay, so neural networks, it's used for supervised learning. So now, as we have seen multiple cases like SVMs in decision trees, as well as I did not go through logistic regression, but logistic regression basically does the same thing. So we have a specific flow in which we go about when we are given a supervised machine learning problem. That is, we get the data set, somebody gives us the data set with X and Y. So these are labeled examples where X refers to the features of all those examples and Y is the set of labels, and we compute some function of X with the help of a learnable parameter W. So we convert the input that is given to us by means of some parameter W, which we call the weight matrix, and we get a function of that, and we say that this is that whatever W we learn from the training examples, that Wx is our predicted label for that particular training example X. And then once we have got this Y hat, the only thing that is left to do is to let the algorithm know that how wrong you are, how wrong the algorithm is at that particular point of time, and with that particular value of W, how wrong it is from the actual class label. And to denote this to the algorithm, we have a loss function, and this loss function denotes how much Y differs from Y hat differs from Y. Okay, so we will do effectively the same thing in neural networks. So the first idea is perform well on the training data, which means that we need to reduce the training loss, and X is given to us. So X is something that we cannot change, X is already given to us. So the only way to reduce the loss is to change the value of W. The only way to reduce the loss is to change the value of W, and therefore can somebody think of any operators that can help us in this particular case? I should frame my question in a better way maybe. So my question is, we need to find out a way in order to find out how much the change in W changes the value of the training loss. So what mathematical operator do we have which helps us to do that, find out the change of change in the value of the loss function with the change in the value of W? What mathematical operator will help us do that?
Activation function, no?
Activation function is something that I have not introduced, that will be introduced to you within the course. Okay, it is something, it's a mathematical operator which all of us know.
Derivation with respect to
W.
Yeah, so somebody said derivation with respect to, yeah, so can you complete your sentence? You are on the right track.
Yeah, so, derivation of the cost function with respect to W.
Correct. So derivation of the loss function with, or the cost function with respect to W will give us the it will give us an idea about how we change, if how much the loss will change if we change W. So that is precisely the operator that we would use, and that is the operator that is used in neural networks. So we choose a W, we compute the loss.
Could you write down that derivation example on the slide somewhere?
Derivation example means?
Just some sir has said na, that someone has said it in the group.
It is, so I have,
It is the derivation with the cost function. No?
yeah, if the derivation is dl by dw. Now, right now L is not defined, W is not defined. So it is just dl by dw. You just keep that in mind as of now. Okay. You don't need to look about, you don't need to think about what should be the value of the derivative. Just understand that derivative is required for this purpose, because derivative gives us the idea about how, if we change W, how much the loss would change. So that was my question. Okay, so then what we do is we choose a W and we compute the loss. So for a given W, we will have some loss function. For this given W, we will have some y hat. From that y hat, we'll compute the loss and we'll calculate the gradient of the loss function with respect to W. So the loss function will be something which you will decide. Again, the loss function. Okay, can everybody please go on mute? I think.
Please mute yourself.
Yeah, I have muted anyway. Okay. So where was I? Yeah. So we choose a W. For that particular W, we go through that whatever WX or some complicated versions of it, and we get for that particular input we will get a particular y hat, which I showed here. We get this particular y hat, and from this particular y hat we compute the loss function, which again you will only decide. So if it's a regression problem, you will choose the mean squared error loss. If it's a classification problem, you will use a logistic loss or the cross entropy loss. So that depends on your particular problem, and then you will calculate the gradient of the loss function with respect to the W. So this gradient of the loss function that you will get with respect to W, that has the property. Okay. Yeah, so the gradient that you have that has the property that it shows the direction, that the gradient shows the direction in which, if you go, the loss function will increase by the maximum value if you go in that particular direction. That is a property of the gradient. So the gradient provides that is meant, that is precisely what I mean by this line, that gradient provides the direction of steepest ascent of the function. Why steepest? Because it's the largest change that you can achieve, and ascent because the function will increase in that direction. So if you go in the direction of the gradient, your loss function will go on increasing. But as you might have understood, loss function is an indication of the error that you are incurring on your particular problem, and therefore the loss function needs to reduce. So because of which, what we do is we go in the direction of the negative gradient. So negative gradient points to the greatest decrease of the function, and therefore the algorithm that is used to solve this particular problem is known as gradient descent. You compute the gradient and then you move in the direction opposite to the gradient. That will change your W in such a way that your loss function goes on reducing. Your loss function goes on reducing means you are performing increasingly well on your training data. Is this clear till now?
Yes, sir.
Yeah. Thank you.
Okay, so then how to compute this gradient? So this will be the bulk of what I will cover today, because this is how it is. I mean, I felt that again deriving one another backpropagation algorithm doesn't make sense. So I will talk about how the idea about backpropagation algorithm came, and then I believe that you would be able to derive the backpropagation algorithm yourself. Okay, so something that is of prime importance in deep learning and I mean machine learning and deep learning is the idea of computational graphs. So if you see all the softwares that are out there, like there are many softwares like sklearn has some very primitive neural network architectures which you can code through sklearn, which is scikit-learn. Then there are other more sophisticated softwares like PyTorch or TensorFlow, These are the most widely used, so I name these two. There might be many more. So these two, what they do is always they will, whenever you will write a network in this particular coding language or this particular format, whenever you will write, they will immediately make out your model into a computational graph, and that computational graph is something that they will store. And whenever you will learn your model, all the gradients will flow via this computational graphs. So understanding this computational graphs, they are very simple, but understanding this is important. So the main question is finding out W by means of the gradient may not be computationally feasible, because in a, okay, I'll explain this why it is not computationally feasible, and as I go along. So in deep learning we do this by computational graphs. So let's start with a very simple example. This is also one of the questions that was given in the last year's assignment. So let's say I have a function which is f of x comma y comma z. It's a function of 3 variables, and once and the value is x plus y into z. So this is pretty simple, and for this the computational graph is as follows. The computational graph is this one. So ignore the numbers that are there for now. So it's quite simple, right? Like you take x, you take y, you add them up, you take z, and you just multiply it with the summed up value of x plus y, and you get a value of f. So this equation can be equivalently represented by this graph. Is this clear to everybody?
Sir, can you define what is computational graph?
Computational graph is precisely this thing which is drawn here. Like this is a computation which you are doing, x plus y into z. All your variables will become inputs, and all the operations that you would do become nodes in this particular graph. So so that is what, so see here you are doing two operations, you are doing a addition and you are doing a multiplication. So these are the two nodes of your graphs, and your inputs are x, y and z. So this is the equivalent formulation of this equation into a computational graph. This is the computational graph that I have drawn.
Soumya, you were talking about the motivation behind backpropagation.
Yeah.
Is this the motivation? And second thing, computational graph, how they are storing your model?
Yeah, I'll tell that. This is the first computational graph that you are seeing. So hold on. I mean, is this clear, right? X plus.
Visually, it makes very easy to understand.
No, it will become clear as to why I said that computational graphs are important. So once I go about more complicated examples, you will understand. This is just a toy example which is just for introducing computational graphs to you all. So is this fine, where how x plus y into z becomes this particular thing?
Yes, sir.
No, sir. Can you explain it, please?
Okay, I'll explain it again. So suppose you are given a particular function x plus, okay, so I'll again remove the computational graph from the screen. Okay, so x plus y into z, this is the function that for which you require the computational graph. So what are the two computations that are happening here? I mean, who asked the question, can you say? What are the two computations which are happening in this particular equation, x plus y into z? Hello?
So
Addition and multiplication. Addition and multiplication.
Addition and multiplication.
Addition and multiplication, right? And what should be what are your inputs for this particular function?
X, Y, Z.
X, Y, Z. So that is precisely what you do. You take x and y, you add them up, you take the summation and you multiply it with z. And that is your function f. Is this clear now?
That is
Yes.
clear, but how this has come 1 equal to QZ?
No, 1 equal to qz, where it is?
Here, what is this?
No, you don't, you just look at the graph, you ignore all these numbers also for now. You just look at the graph, x, y, z plus and multiplication, that's it, nothing else.
That we got, but this down calculation.
Yeah, down calculations I'll come to the down calculations now. Okay.
Okay.
Yeah. So now let's say the inputs are x equal to -2, y equal to 5 and z equal to -4. That is what is, suppose the input, somebody has come and given you these inputs, x equal to -2, 5 and -4. So these are the three inputs that I have talked about. So the inputs I'll write at the top of the particular arrows. Okay, the bottom of the particular arrows will be reserved for gradients. So I'm not talking about gradients now. So just consider the top values to be the inputs. So as you can see, -2, 5 and 4. So -2 and 5 after getting added gives you 3, and which being multiplied by -4 gives you -12. So you get your particular, for this particular value of, for these particular values of x, y and z, you get the particular value of f to be -12. Now all you need to, now what you have been asked to do is, you find out the value of df dx. You find out these three values, dou f dou x, dou f dou y and dou f dou z. These are the partial derivatives, means that when you are considering the change of f with respect to x, y and z will remain constant. Similarly, when you are taking dou f dou y, x and z will remain constant. When you are taking dou f dou z, x and y will remain constant. So only that particular value which is there in the denominator will change. That is the definition of partial derivatives. I hope you are clear with all of these before, because these are basic calculus stuff. So name the intermediate variable q. You may not name it, but just for convenience, now let me write the intermediate variable by q. So the intermediate variable q is given by x plus y, which you can see that q comes out after you have added up x and y. So q is simply x plus y. Okay, now since q equal to x plus y, dou q dou x will turn out to be 1 and dou q dou y equal to 1, because q equal to x plus y, so dou q of dou x means y is constant. So this basically it, dou q of dou x will just give out, is just the derivative of x plus y with respect to x, and therefore it is 1. Similarly, dou q dou y is also equal to 1. Finally, the value of the function f is equal to q into z, and therefore dou f dou q will be equal to z, because at that particular point when you are taking dou f dou q, z is considered to be constant, and therefore dou f dou q will be equal to z and dou f dou z equal to q. Okay, so these derivatives.
Second line, please repeat.
Which one? This f equal to qz one, is it?
Yes, sir. Yes, sir.
Yeah, so when you are taking f equal to qz and you are taking dou f of dou q, as I said, dou f of dou q considers z to be constant. So it is, you can think of, you can consider this z to be a constant and q is the variable here. So dou f of dou q will be equal to z. Is that clear?
Yes, sir.
Simple derivative.
Yeah, this is a simple derivative with the other constant. So and dou f dou z will be q. So now, so you have got all these, I have given you all the things. So can somebody tell me what would be dou f by dou x? I mean in terms of the variables, don't give me the value now. What will be dou f dou x?
Y plus z, yz.
Dou f dou x will be yz. Okay.
Yz.
Why?
Because here x will be varying and yz is constant. No?
See, f dou f dou x. Okay. Why will it be yz again? I did not.
Yz will be constants and x will be varying.
No,
yz will be constant and x will be varying, that is right, but you need to look at how f is defined, right? X is defined as x plus y into z, and you are changing only x, y and z are constant, and you are taking the derivative with respect to y.
So df by dx is equal to df by dq into dq by dx.
Correct. So what is this called, what you just said?
df by
No,
dx.
you said correctly. I am saying that what is this particular rule called, what you said? You applied some rule.
Chain rule.
Correct. So that is the chain rule that we are talking about. Okay, so this is again from basic derivatives. So see, what you need to do is, you have already, so if I say here that f of x comma y comma z is x plus y into z, so that is again q into z. As I have denoted x plus y as q, So the first thing that you need to do is you need to take a derivative with respect to q, that dou f of dou x can be written as dou f dou q into dou q dou x. Okay. See here, the rightmost term which I have written, that is the chain rule that I am talking about. That dou f dou x can be written equivalently as dou f dou q and dou q dou x, which is precisely equal to -4. From here also, if you just take xz, if you break this up into xz plus yz, then you would get the same thing. What would you get if you break this up into xz plus yz and take a partial derivative with respect to x? What is the value that you will get, or what is the variable that you will get?
Z, sir.
I did not hear you. What did you say?
Z.
Z. And what is the value of z in this example?
-4.
Exactly, and that is the exact same thing that you are getting here. Okay. So dou f by dou x equal to dou f dou q into dou q dou x, which is dou f dou q is equal to 1, as I have dou f dou q equal to z, and dou q dou x equal to 1, and therefore -4 into 1 will become -4. And dou f,
Soumya,
yeah.
Could you tell us the chain rule, please? I forgot the rule.
Yeah, it is you can see my cursor, right? So this is the chain rule. So dou f dou x, if you have x is directly dependent, q is directly dependent on x, therefore you can do this as dou f dou q into dou q dou x. Or if there are multiple variables, you could have taken dou f dou q into dou q dou dou p into dou p dou x. You can break up your derivatives in that form. So in this case, f is directly dependent on q, f is not directly dependent on x. So in order to, you look at the computational graph, what you need to do is you need to find out the change of this variable f with respect to this variable x, and f is not directly dependent on x. Therefore you need to first find out how much f will change with respect to q, that how much. So that will give you an idea that if q changes this much, f will change that much. And once you get the change in q, then you would find out how much if I change x will q change, and therefore indirectly it will start affecting f. Can you see this line here? I mean, did you understand what I just said?
Yes, I
Sorry,
understand.
sorry, Soumya, how this df by dq has come as -4? Earlier we have calculated as 9, na? df by dq equal to, okay, sorry.
df by dq is calculated as z, and z equal
yes.
to -4. Okay.
How the z is -4? Where it has from?
Z is the example is starting with z equal to -4.
Yeah. Oh yeah. Sorry.
Okay. Yeah. So this is another way that I wanted you to look at this particular computational graph. I mean, this is very simple from this example, but these intuitions will help you if you go on doing any stuff with deep learning. One thing is, you always try to find out whenever there is some I mean, you will see these cases in more complicated examples. You may face these situations, like you won't understand whether x has direct effect on f. So you need to go through this, you need to understand this computational graph, because x is affecting q, and q indirectly is affecting, and q is directly affecting f. So in some sense x is indirectly affecting f. So and this indirect effect which you are thinking about is written mathematically in the form of chain rule. So you see, x is directly affecting q and q is directly affecting f, and on the left hand side you have x indirectly affecting f. So that is how chain rule comes into the picture, and the others are pretty simple, like df dq, dou f dou q is simply z, so that is -4. I have already written that, and dou f dou z equal to q, which is 3. You can find dou f dou y in a similar way. Dou f dou y will be the same thing as it will be equal to -4 again. So these are how computational graphs are computed or used. So one thing which I would like you to look at keenly is look at the multiplication gate and the addition gate. So these are the two gates which are here. One is plus and one is this particular multiplication. So you see one thing, you have calculated something, you have done everything correctly. Now just see what is coming out from here. Dou f dou z, which is the change in the value of this particular variable z, that is turning out to be 3, which is the value of the other function with which it was multiplied. And dou f dou q is turning out to be the value of z with which it was multiplied. So you can think that whenever you have a multiplication gate, so it's like as if you are switching the two gradients. Is this point clear? I mean, this is an intuition. It is, is this intuition clear?
Please
Will
repeat the
you-
last sentence.
Please repeat, yeah.
The last sentence.
Yes, yes. So you can understand this thing, right? Like q and z are multiplied to give f. When you are computing the derivative, you see that the dou f dou z, that is the value, that the change in the value in this particular variable is actually governed by q, and the change in the value of q is being governed by z. Is this clear? Is this point clear?
Yes, sir.
Yes. So if
Yes.
so if these points are clear, this means that this multiplication is doing a sort of switching at its end. So so the change in the, so if two variables are multiplied, a and b, then they are multiplied in a way that so the changes in that particular variable of this, so the change in q in this case is dependent on the value of z, and the change in z is dependent on the value of q. So this is a sort of, this is an intuitive way of thinking this as a gradient switching sort of a way, that the how much I will change z will actually depend on q, and how much I will change q will actually depend on z. Okay.
Yeah, in a sense, we can infer that. That is
Yes.
correct. It's happening also just by virtue of the derivative function
Exactly, exactly, exactly. So that is one important point that I mean these are just good intuitions to have. It is not as if this will help you in solving any problems, but these are good intuitions to have. The other good intuition to have is this addition sign. Okay, somebody is trying to join. Okay, yeah. So this addition sign which you are having, okay, believe me when I say that dou f dou y is the same as dou f dou x. So dou f dou, you can come, it's a small calculation like dou f dou q into dou q dou y. So again it will be -4, because dou q dou y is also 1, which is the same as dou q dou x. So this plus sign is behaving differently to this multiplication sign. Whatever gradient you had here, they are changing both of these x and y similarly. Is this clear?
Are you trying to say, sir, that if the value of, say, one variable of the addition input changes,
Yeah.
it will not be affected by the other, or like it will be similar, the other will be also similarly affected?
Yeah, the second point is correct, which means that if you just look at this function, you have some particular value of z, okay, and you have x and y. It doesn't matter whether you increase x by 1 or whether you increase y by 1. Both of them will give the same value of f, or the change in the value of f will be exactly same, and that is given by dou f dou x equal to dou f dou y, which means that this plus sign is actually so you can think of this computational graph in a backward sense, like the gradient is coming from, because generally at the f side f will be a loss function. So when you have the loss function here, there will be some gradient here, you will calculate the gradient here, and it will start flowing and change your weights and whatnot. It will start changing everything. So you need to look at this in a backward sort of a way, like you need to come from f to xyz. So once you have come up to q, this plus sign will change x and y equivalently. Plus sign won't favor x or y, unlike the multiplication sign which affected q and z differently. Plus sign affects x and y in the same way. Is it clear now?
Yeah, but sir, it is an inference looks like. But if we try to understand it from changing the value, for example, if I change
Yeah,
x minus 2 to minus 3,
yeah.
you are saying there will be no impact on f because of that?
No, I'm not saying that. I am saying that if x, if you are changing, let's say you are changing x from minus 2 to minus 3,
Correct.
and in another example you change 5 from 4, 5, you change y from 5 to 4, the value of
effect will be same.
the value of f that you will get is same.
Ah, okay.
Okay, so that is precisely what I want. I mean, these are pretty simple examples to look at, but in machine learning sometimes these things help, because okay, I won't say more about this. So the thing is, just remember that whenever you have a plus sign, and the gradient has come up to here and the gradient has to flow back to x and y, it will affect both x and y similarly. It won't favor one over the other. That's the only point that I wanted to make. Okay.
Sir, one doubt.
Yeah.
How did we get this 1 equal to QZ? I missed. I think
1
I missed
equal to q.
QZ.
Oh, that is not 1. Sorry for my handwriting. That is f equal to qz actually.
Yeah, this is f.
That is f equal. That is f has gone. I mean, so that is f equal to qz. That is not y equal to qz. 1 equal to qz.
Thank you.
Okay.
Sir, the
Yeah.
way multiplication has affected, I mean, dependent on the other variable, same way division also might be affecting the other variable.
Division also will affect in a similar way. I mean, you can work out the division rule yourself. I mean, it will be it will just be normal derivatives. So you can work out the division rule yourself. It will affect in the same way. It will be dependent on the other variable.
Got it.
Okay. Okay. So now.
Soumya,
Yeah.
last one
Yeah.
more thing.
Yeah.
Dou q by dou x you have written as 1. Why you have equated to 1 in the here?
Dou q by
bottom.
yeah. So q equal to x. Q equal to x plus y. Correct. So if you consider y to be constant, then q equal to x plus 5 in this case. So what is the derivative of dq by dx in that case? Am I clear or am I not making sense?
So it will give one value if because y is constant. That's
because y is constant, then dou q dou x equal to 1.
okay. It will give you one value, right?
Yes.
Okay. Good.
Okay.
Thank you.
Okay. So now this is a toy. Yeah.
Excuse me.
Yeah.
So if x changes, that there is no change in f.
No, that is not the point. I mean that dou f dou x and dou f dou y is the same, which means that if you change x or if you change y, the value of f will change similarly, or by the exact same amount.
Oh,
Okay. Yeah.
okay.
Okay, so now let's go on to a more complicated example. This is taken from a Stanford lecture which is quite famous. So okay, so now this is a more complicated example. So here we have w0, x0, w1, x1 and w2. We have 3 w's and 2 x's, and we do this particular function, that 1 by 1 plus e to the power minus w0 x0 plus w1 x1 plus w2. Okay, this is the particular function that we are talking about. Don't consider these values as of now, just look at the graph. The green and the red, both of the values you don't consider now. So we have w0 into x0, we take a multiplication of that, that is the first term in the exponential in the denominator. Similarly, we take w1 x1, we do a multiplication of that, we add them two up, we add these two up, w0 x0 plus w1 x1 by this particular addition. Then we add w2 to it, then we multiply minus 1 with this particular thing, which is minus w0 x0 plus w1 x1 plus w2. Then we take exponential, which is this exponential, then we add 1 to it, and then we take a 1 by x of it. I mean, what 1 by, because this is the particular function that we are talking about, so we take a 1 by x of it. Is this clear how this equation becomes this particular graph? It's precisely the same thing that we have done in the previous slide, just on a bigger example. Is this clear?
Absolutely.
Yes, clear.
So, sorry, once again,
Yeah.
how you got 1 by x?
1 by x is, see, till here you understood that it is this denominator, right?
Yeah.
So the final function is 1 by this denominator. So that is why you do 1 by x. This 1 by x means whatever comes to its input, you just take a 1 by that of,
Okay,
of that.
okay, sorry. It's 1 by 1.73, no? Okay.
1 by
37.
1.37, correct.
Yeah,
Yes.
okay, thanks.
Okay, so now,
One doubt,
yeah.
this W2 connector,
W2 connector, yeah.
W2, if you connect to left side plus, I mean, is there any difference? Why you have connected this separately? Can we connect
No, it
this?
doesn't make a difference. It doesn't make a difference. It's just that the way the person has drawn this is like he or she has taken the addition to be of two. It can only have at max 2 inputs maybe. That is why he or she has drawn it in that way. But additions can have multiple things, so you can add up W there or W2 there as well. Doesn't matter.
Okay.
Okay.
And other doubt is,
Yeah.
you have this, how you are getting the minus in the sigmoid function,
Yeah.
okay? The e to the power minus, where is this minus getting represented in this computational graph?
You see here it is. I am doing a multiplication by -1.
Thank you.
So yeah, so one more thing which you correctly pointed out, this is precisely the sigmoidal function, but this is the sigmoidal function in its full glory. I have removed everything from, nobody will think that this is a sigmoidal function at the first go, looking at the computational graph. So I've just drawn it in that way. I mean, the person has drawn it in that way in order to explain how a computational graph works. Okay, so okay, so now we need to look at the numbers. So the green ones are the inputs and the red ones are the gradients. So the green ones are something which are known as the forward pass. So whenever you have you will have a neural network. Let's say this is a neural network. This can be a very simple neural network, and this won't help you do anything, but still you can consider this to be a neural network. And so what you can do is, first what you need to do is you need to have some inputs. So let's say x0 and x1 are my inputs, and w0, w1 and w2 are the weights, and these are the weights that you have initialized. You have just initialized 2, -3 and -3 as your initial weights. These are the weight initializations that you have done, and the first thing that you will need to do is to do a forward pass. So these green numbers, as I go on moving on along this computational graph and filling up these green numbers, this is known as a forward pass. So why forward pass? Because you are going in the direction of these arrows. So what you do is, you have x0, you have x1, you have initialized w0, w1 and w2, and you first compute w0 x0, it comes out to be -2, you do w1 x1, comes out to be 6, add w2 to that, add to these two, you get 4, add w2 to that, you get 1, you do -1 exponential, and finally you get 0.73. So coming from -1 and -2 as your inputs with these particular initializations and going up to 0.73 is known as one complete forward pass in the model. Is that fine?
Yes, sir.
Okay. So
Absolutely.
now what you need to do is, you need to find out the derivative of this particular you need to find out the derivative of again you are doing the same thing as the previous example. In the previous example you were trying to find out the derivative of f with respect to x, y and z. Here also you will try to here also you will try to find out the derivative of this particular function, which is f of yx, and as a value of 0.73 for these inputs and initializations with respect to all of them, w0, x0, w1, x1 and w2.
But sir, there is 2 input now, so there should be a derivative with respect to x0 and x1 only.
No, first of all, you cannot take derivatives with respect to inputs, because that doesn't, you cannot change your inputs. Okay, So you that's the first thing. So the only things that you can change are W0, W1 and W2. So ideally you should take derivatives only with respect to W0, W1 and W2. Am I correct?
Okay.
Yeah, but
Got
I'm
it.
saying here dx, I am saying you compute the derivatives with respect to x0, x1 because this is not a neural network. Okay, I mean I just told you that this is a neural network in order to give you some idea, but you are correct. When you are truly doing this from a neural network point of view, you won't take the derivatives with respect to x0 and x1 because you can't change them. That's the only reason why. Okay, so now you have this 0.73, the value that you have computed, and the derivative with respect to that is 1 because dou f by dou f is always equal to 1. It was similar, it was same in the previous slide. You see dou f by dou f equal to 1. So here also dou f by dou f will always be equal to 1. So that's trivial. So now you need to, so now your derivatives, now you can go from this 1 and you have to come up till w0 x0. So you have got this 1, now you need to get to minus 0.53. So okay, can somebody say how this minus 0.53 comes? I mean okay, so I'll say maybe because this might be a bit difficult for you. See, you can think of the input to this 1 by x function as q. So like I showed here, you had q. So here also you can think of this particular function as q, 1.37. Let's say q equal to 1.37, and upon doing that 1 by x, your final value became 1 by q. So f is essentially 1 by q. Is this correct? Is everybody clear with this?
Yes.
Yes.
Okay, so if f equal to 1 by q, then what will be dou f by dou q?
Minus 0.53.
Sir, what is f? What is f equal to?
F equal to is written on the screen, right? F is this function 1 by 1 plus e to the power. F is the output of this computational graph. So if you have f here and if you have q here, then f becomes 1 by q. So what is dou f dou q? From normal derivative rules,
It will be a constant, no?
dou f dou q will be constant, is it? F equal to 1 by q. So what will be? Don't think about dou f dou q. Think about df dq.
Plus 1.
Minus q.
No, I'm not asking about values.
Minus 1 by q square.
Yes, it should be minus 1 by q square. That is the derivative of 1 by x. Am I correct? I mean, is this clear?
Sir, we have forgot all the basic derivatives.
Yeah, you would. Yeah, you would need to understand the basic derivatives here. That 1 by x equal to. So basically, how can I say? So basically, the derivative of x to the power n would be nx to the power n minus 1. So you put minus 1 there, you would get minus 1 by x square. Okay. So you would need to, all you need to do to understand back propagation is to understand the basic derivatives. You just remember the basic derivatives, everything would be fine. Other than that, there is nothing in this entire big algorithm. Okay, so as somebody said, it would be minus 1 by x square, which in this case would be minus 1 by q square. So minus 1 by 1.37 square is the derivative with respect to dou f dou q. And dou f is always equal to 1, so doesn't matter. So if you do minus 1 by 1.37 square, you would get minus 0.53. That is the derivative that you that is the value that you get here. This is the derivative that you get here. Okay. So now if you get minus 0.53 here, can somebody say why this should be minus 0.53 again? I am just doing a plus 1 here. So why is this minus 0.53?
Derivative of e power x is
no, I'm not talking about, I have not gone up to e to the power x. I am at the plus 1 block now. So this is one node that I have, at the input of this plus 1 block is minus 0.53, and now I have to give the output of this plus 1 block. It is, the result is shown, it is minus 0.53 only, but why?
Plus 1 doesn't vary, that's why.
That is true, but okay, so I should have let me see, what can I do? Yeah, at this you can see the particular I am marking something on the screen, right? You can see that, right? Or is it not visible?
Yes.
Yeah, yeah, okay. So here what I had written was, I had written the variable q here, correct? Q was written here, and this became 1 by q, the output became 1 by q, and because of that derivative it became minus 1 by q square, and therefore minus 1 by 1.37 square. Similarly, if you write here, let's say what can I let's say you write here z, then what is q? If I
Z plus 1.
Z plus 1, then what would be dou q dou z?
So f by dou z, no?
1 only.
Yeah, no, I am not talking about dou f dou z, I am talking about dou q dou z, which she said is plus 1. Then how do you find out dou f dou z? Hello? Yeah, you have already found out dou q dou z, and you already know dou q dou f, dou f dou q. So how can you
So by
find?
using chain rule.
Again by using chain rule. Okay, so this is the crux of the entire backpropagation algorithm or any training neural networks. See, one great advantage that you are getting here is, if you are breaking the entire computation in this way, even when you are trying to find out the gradient with respect to this node, let's say, you don't require the gradient of any of these nodes. You don't require the gradient of any of these nodes. All you need is the gradient with respect to this node. Is this concept clear?
Yes, sir.
Okay, I am asking again, is this concept clear to everybody?
So are you saying that a plus will, because of the addition, the remaining is not required?
No, I am not saying that. Okay, I'll go along. So I'll come to you will understand you will understand my point better in the next node maybe. So this part is clear, right? That why dou z dou q, while dou f dou z is the same as dou f dou q.
Yeah.
This
1 into minus 0.53, it becomes like that.
Yes.
Chain rule.
So let's say so now we have gone up to the exponential block. So the exponential block is getting an input of minus 0.53, and you have to give the output from the exponential block. So so again, if you consider, I am running out of variables, but if you consider this as y, then what is z? What is z?
E raised to y.
Z is nothing but the exponential of y, correct? So what is dou z dou y? Z equal to e to the power y, okay, z equal to e to the power of, okay, it was gone now, y.
It is y e raised to y.
Minus 1, z raised to minus 1.
What is the derivative of, I can't write this, I don't know why, it's better if I could have written, okay, no, let me see whether I can write something here, no I can't, anyway, okay, I'll close this, yeah, so z equal to e to the power of y basically, okay. So what would be dou z of, so don't consider dou z, what will be dz dy? So if you have an exponential function, what is the derivative of the function?
It will be the exponential
function itself, correct? So
Yeah.
the derivative of e to the power of y with respect to y is e to the power of y itself. So dou z dou y will become e to the power y, but you needed dou f dou y. So now what you will do is you will take dou f dou y and you will break it up like dou f dou z into dou z dou y. Dou z dou y you have calculated here by e to the power of y, and dou f dou z is you already know from the previous block. So now is my point clear that it was not only because of the plus 1, but it is because of the way we have written this particular thing. Is this clear now? Somebody
Yes,
asked.
sir.
Somebody
Yes, sir.
asked this question, right, that is it only because of the plus 1 block? So once you have come up to the exponential block, you don't need to remember any of these things, that plus what derivative you had here. You don't need, for example, for finding out this minus 0.20, you just require this minus 0.53. You don't require this minus 0.53, you don't require this 1.
Absolutely clear, sir. 100%.
Yeah, so now we are getting minus 0.20 as at this particular point, and so now things should be pretty simple. Now it is like now if you have a p here, let's say I call this as p, so
Yeah.
y equal to minus p, so the derivative of y with respect to p would be okay. You guys need to get hold of derivatives, or maybe I have not written it, that's why it's not
Concept is
clear.
clear. Concept is clear. Derivatives are not clear, but concepts are clear.
Yeah, see, this is y equal to
Minus p.
minus p. What will be the derivative of y with respect to p?
Minus 1.
Minus 1. So similarly, as you had done before, you take this minus 0.20, you forget minus 0.53 and all, you take this minus 0.20 and just multiply it by minus 1 and you get 0.2. Okay. Now as I have already told you that this there is a positive, there is a plus sign here, so you don't need to do anything else. You just whatever you had 0.2, you put 0.2 here, you put 0.2 here, because I showed that in the previous example. So plus sign will just give the same gradient to all of it. So minus 0.2 comes here, minus 0.2 comes here. You have already found out the derivative of dou f with respect to you have found out the derivative dou f dou w2. That is the first derivative that you have got. So
Right.
you get 0.2 here, again 0.2, since there is a positive sign here, there will be 0.2 0.2, so again plus distributes them equally, so 0.2 and 0.2 comes here. Okay, now there is a positive, now there is a multiplication sign. So whenever you are getting a multiplication sign, one thing which you need to do is it should be dependent on the other value. Okay, so here, okay, yeah, here if you had here if you notice, when the multiplication sign was there, dou f dou q became equal to z, and dou q and dou f dou z became equal to q. So that is the exact, okay, it is gone now. Oh, okay, it is there. Okay, so so that is the exact thing that will happen with respect to dou f dou w0. Dou f dou w0 will see this input coming as 0.2 and it will multiply it by minus 1. Is this clear?
Yes, sir. Very much.
See, again, if I write here m, so m is nothing but this, okay, it is, I don't know why it is straightening up, but okay, m is nothing but this w into this particular x. Now x is not coming for some reason. This is very I don't know how to put, okay, w into x, let's say this is w into x. Now consider this to be w into x. So if this is w into x, then when you take the derivative with respect to w, it will be x, and when you take the derivative with respect to x, it will be w. So basically this 0.2 will come, it will get multiplied with the other thing, and that will be the gradient. So this should be ideally 0.4, but I think there are some approximations going on here, but so this should be 0.4 and this should be minus 0.2. Similarly, if you see 6 coming in here, sorry, 0.2 coming in here, then 0.2 getting multiplied by minus 3 will give you the value with respect to x1, the gradient with respect to x1, and minus 2 getting multiplied 0.2 getting multiplied with minus 2, which is
0.90.
0 point, again this should be minus 0.4, but okay, so there are some approximations because of the exponential maybe. So because of that, this is coming out to be minus 0.39. So is this entire computational graph clear to everybody?
Yeah.
Yes.
Very interesting, sir.
Yeah, so the major advantage that you are getting here is when you are looking at a node, you just need to look at the neighborhood. You are not looking at the nodes which came before your neighboring node, basically. That is the advantage that you are getting if you are doing this by means of a computational graph. Okay, so
Sir, 1 minute.
Yeah.
Sorry to ask.
Yeah.
Everything I got, only this last gradient, how it has come. Somehow I missed that.
Yeah, so m equal to w into x, this much. So m is the variable.
No. Here at the last. After 1 by x, you have written 0.73 and gradient is 1. Last.
Oh, that is f, right? So dou f equal to 1. The derivative of a variable with respect to itself is equal to 1.
Okay.
That is precisely f. So that is why you are getting dou f equal to 1. Okay.
That is dou f.
Yeah. So that is.
So please repeat.
Soumya?
Yeah.
If you consider the plus sign here at the layer 2.
At the layer 2, which plus sign? This one.
Plus sign. Below above that.
This one.
This one. And if you apply the thing which you have explained for the this input layer, how it will work now?
What did I explain for the input layer?
Here for W0 and X0, what you have multiplied and you got the final values now here. Just like that, if you apply for this plus sign,
plus sign
0.20, if you are multiplying with this, let's say 6.
No. See, plus sign distributes the gradients equally. That is the difference between plus and multiplication, right? That is what I showed in this example also. So when you had a plus sign, dou x and the gradient which was coming here, which is dou f dou q, is the same as dou x. They are equally distributed between x and y. You see, dou f dou x and dou f dou y in this example was same. When you are encountering a multiplication sign, then there is a dependence on the other value. When you are getting the plus sign, because of this, because of the way we calculated, and because it is true also, that q equal to x plus y. So when you are doing x plus, since you are doing q equal to x plus y, whatever gradient will come to q will be distributed equally between x and y.
How it will be applied to the problem at hand, which I have asked you there? How the weights will be changed?
See, here the 0.2 is coming, right? So they are equally distributed between the two arms of this addition.
Okay.
So that is the point.
It will happen in subtraction case as well?
Subtraction case, it will be x minus y. So subtraction case, again, if you want, you can do something like, when you are doing x minus y, you can multiply y by minus 1 and then add. Okay.
Slightly different, yeah, I got it.
So one variable will reduce, the other variable will increase. But if you are trying to put subtraction into this particular graph, one way would be you are subtracting x minus y. You multiply y by minus 1 and then you add with x. That's the same thing.
Got it.
Okay. Okay, so I hope this graph.
And so please repeat m equal to w into x.
That
part is troubling me.
So I have written it in a troubling way also, but okay, so m equal to wx. So what would be dou m dou x? Hello? Yeah, that would be w. Dou m dou x would be w. So m already, you already know dou f dou m. So dou f dou x would be dou f dou m into dou m dou x. Am I correct?
Yes, sir.
So you already know dou m dou f dou m, which is 0.2 in this case, and dou m dou x is precisely w. So you are multiplying this 0.2 with w to get 0.4. Okay.
Sir,
Yeah.
We understood if multiplication or addition are there at the node, how we can find out the back propagation using gradient. But what about division and subtraction? You told about subtraction, but I didn't understand.
Subtraction, one thing which you can do is, suppose you are doing a subtraction of x minus y, so you first multiply y by minus 1 and then you add. So it's basically the same thing. Am I clear?
Once again, sir.
Suppose you are doing x minus y.
Okay.
So one thing which you can do is, you take your inputs x and y, you multiply y by minus 1, which I have done here also. I mean, I have done that minus into minus 1, and then you put a addition with x.
Okay.
And subtraction you can do again. You can first, suppose you are doing x by y, you take y, you pass it through 1 by x block, you get 1 by y, then you add, then you multiply with x, you will get the same thing.
Okay.
So basically in this computational graph, you have everything that you log and all those things are probably not there, but you can take everything more or less. All this computational graph covers almost all the computations that you will be required to do.
What about division?
Yeah, division I just said, right? You take, suppose you are doing x by y, so you take y, you pass it through a 1 by x block, this last block that is there on the screen, 1 by x block, then y becomes 1 by y, then you multiply with x.
Okay.
Okay. Yeah.
Sir, last thing, in the reverse calculation,
Yeah.
you will always have 1 on the right side, top right side, right?
Top, bottom right, yeah, this one, yeah,
Like,
the first block is trivial.
Right side.
Yeah, that is trivial, that is always 1.
Always. And
Yeah.
it's like something we are now trying to calculate the impact of the inputs or the labels based on consideration that the final outcome is 1. So how it is going to be impacted with the inputs? That's how we are trying to.
Yeah, so finally, so so ultimately what you will do is, you will have a loss function at the end. Okay, you will have a loss function at the end. So you will have, so as I said, you will have an input, you will pass it through some neural network layers, you will get y hat, and this y hat you will combine with your original given labels of y, and you will compute a loss. This loss function, you will the first step would be to find out the derivative of the loss function with respect to this y hat, the one which you have predicted and one which you have control over. So once you get this dou f by or dou L, so if I denote the loss function by L, so once you get the loss function, the derivative of the loss function with respect to what you have predicted, which is y hat, then you do the entire, then you do the thing which I have shown. Am I clear?
Yeah, sir.
Yeah, so once you do an entire backward pass, you will get all these gradients. These are all gradients. What does this gradient show? That this, for example, this minus 0.2 to w0 shows that if you change w0 by, let's say, 1, your function value will reduce by minus 0.2. Is this clear?
Absolutely, sir.
Now as I said, I mean the initial concept was to go in the opposite direction of the gradient. Everybody remembers that. Always remember that you are going in the opposite direction of the gradient. You are calculating the gradient to be minus 0.2. So if you are supposed to go in the opposite direction of the gradient, you would actually increase w0 by you will actually increase w0, because the reduction in w0 is actually increasing f. So that is another concept that you need to understand, that once you have calculated the gradient, you need to go in the opposite direction of the gradient. Okay.
Till what time, sir? Like
till what time means, yeah, so that is a question. So that depends on how much longer your validation accuracy improves, So how much longer you will go on doing that, that is an hyperparameter. So hyperparameter is something that is means something that is actually your choice. So you so that is known as the number of epochs that you run. So you can, that depends on your data and your performance on the validation set. So depending on your validation set, you will set the number of epochs that you run your algorithm for.
Okay.
Okay, so I'll move on. Yeah, so I have already shown all of this, like this, how this comes to be minus 0.2, and how all these different values are calculated. So I'm not going through them again. Okay, as somebody said, this entire thing, that from this minus 1 to 1 by x, that is nothing but the sigmoid function. So if you see, the sigmoid function is 1 by 1 plus e to the power minus x. So that is precisely what is done by this. You get x here, let's say you get x here at this particular point, let's say you get x, you multiply that by minus 1, you take exponential, you add that with plus 1, and then you take a 1 by x. So that is the sigmoid function that we already know. So sometimes when you have this sigmoid functions, then your algorithm will know that, okay, this is a sigmoid function, so they already know the derivative of the sigmoid function. So what is the derivative of the sigmoid function? So d of sigma x by dx, 1 by 1 plus e to the power minus x whole square. So it would be 1 by 1 plus e to the power minus x whole square to the e to the power minus x. So I don't know whether this is clear to everybody, but just believe me that this is the derivative of the sigmoid function. You can work it out later. And so this you can break it up in these two parts, that e to the power minus x by 1 plus e to the power minus x into 1 by 1 plus e to the power minus x. So 1 by 1 plus e to the power minus x becomes sigma x, and 1 minus, and this, the first term is nothing but 1 minus sigma x. So this is a pretty standard computation, and all and you might as well remember this completely. So you don't need to, and you don't need to do these calculations every time. The derivative of the sigmoid function is always the sigmoid function itself into 1 minus the sigmoid function. So that is the derivative. So in our example, we had up till here, we had this 1 and we had this 1, and then we did the sigmoid function, and it gave us 0.73. Now when we are doing the back propagation, we went through this 1 minus 0.53 minus 0.53, 0.2 and minus 0.2 and then 0.2. Since you already know that this is a sigmoid function, you can collapse all of these blocks, these last 4 blocks, and make it to the sigmoid function, and you can just compute the derivative in this way, which is 0.73 into 1 minus 0.73, and that comes out to be 0.2, and of course this matches with the value that you have got by this extended calculation. So
shortcut.
Yeah, so this is a shortcut. This will be the simplification that PyTorch and many other and all other deep learning softwares will do themselves. But just know that these this is I mean, the computational graph that I showed you is very primitive, and most softwares will do something very intelligent to reduce the number of computations that you are doing. Okay. Okay, so there are some patterns. The first pattern is, so as I showed, this is a gradient that has come up to the plus block. Whenever you get a plus block, they just distribute equally. You get a g and g here. So g and x and y will both get the same gradients since you have a plus block here. Now one tricky question is, suppose you have x and y and you have a max gate here. So this is a max of x and y, and you get a gradient here. So can somebody tell me which one of this, I mean, what would be the values of the gradients in x and y? With these are the forward values that I had. X was 1.
It should be 2.
These are reverse, no? Reverse. For x it will be 2, and for y it will be 1.
Why will it be reverse?
Because here, if you consider the max as
you are on the right path. You are on the right path. You have to think on that path. I mean, your answer is not correct, but you are
just like the plus node. I have applied that logic here for the max. Because here again we are multiplying q by taking the.
You are not multiplying here. You are just taking a max. So you are
Dou q
taking
by
two
dx.
values. You are taking two values.
Dou
Okay.
q by
Uh,
dx, it will give you
Yeah, are you saying so?
y.
First we take the max, that 1 and 2, max is 2. Then we calculate the gradient d by dx of max, which is 2. That is 1. Now 1 is there for both of them.
Yes.
Is
okay.
that
Dou q
So
by dou x is equal to y, and dou q by dou y is equal to x, like this.
dou q by dou x equal
X
to
is equal to y.
y. Why did you think that?
Here we are taking the value of x as 1 and we are assigning to
Okay,
y.
so let me go into a bit of detail. See, I have marked out these two values, correct? 1 and 2 I have marked out. You can see that, right?
yeah?
So these are the forward values. So tell me, if this output is q, then which of these two values will affect q? X or
Both.
y? Why will x affect y? Why will x affect q?
Y is 2 and x is 0. At x it should be 0.
Y is 2. I mean, you are talking about gradients, or
Gradients.
you are correct. So I want so is this intuitive to others, that y the derivative with respect to y should be g, and the derivative with respect to x should be 0? Okay, I understand that this is not clear to most of you. So okay, now think of this particular what should I say? Okay, let me see. Yeah, so think of this particular graph in the form that who affects my output variable? My output variable here is q. So who is affecting my output variable? In this
Y.
case, there is x and there is y. Hello? Hello?
Both x and y.
Why is x affecting the output variable? That is the point that I wanted to ask. See this.
X is not affecting because the function is maximum of x and y. So always y is affecting in this case.
In this case, for these particular values of 1 and 2. Is this clear that x is not playing any role about what q, I mean, you will have some dou f, dou q, and whatever you will do to x won't change the value of q. Therefore, there should be no gradient passed on to x. Is this point clear?
Yes, clear.
Okay. Is this point clear to everybody? I mean, I know this is slightly tricky, but
Max function, this is not a plus function.
this is not a plus function, this is not a multiplication function. What you will do is, you will take x, you will take y, and you will take a max of them, and you will go on calculate q. Then with q you will do something, you will take exponential, you will do something, and you will get the final value of f. Now when the gradient is coming back, you should change q. You should so q has changed. So for example, dou f dou q will have a role. Dou f dou q implies that, okay, if my q changes, then f will change. That is why maybe dou f dou q will have some non-zero value. Dou f dou x cannot have a non-zero value, because however you change x, okay, if you change x, if x was more than y, then x could have played a role, but x is not more than y. Therefore x did not play any role in the calculation of f, and therefore dou f dou x should compulsorily be 0 in this case. Okay, I hope it is clear. So the other thing I will skip for now. I don't think that you will require it for now. So these are anyway quite complicated, so I'll skip, because okay, so there is one more thing which I had thought of, I had thought of doing a example from matrices. So is it okay? I mean, it is already 5:20, so
It is okay.
it is
Let's
okay.
Yeah, let's do it.
Okay. So I thought about doing matrices because this is the actual thing that will happen in deep learning, or everything will be a matrix. So let's say my f of x comma w is w into x, the norm. This is wx, the norm, the 2 norm of wx, and squared. So x is a vector in the nth dimensions, and W is a matrix of n cross n dimensions. So a toy example would be W would be a 2 cross 2 matrix and X would be a 2 cross 1 vector. You just multiply them with this particular with this particular operator. You get Q, and then you do a L2. L2 is nothing but to take the 2 norm and square. Okay, so that is the definition. So what is the definition? How do you define Q? Q is defined as Wx. So if you break this up into n cross dimensional, the entire broken up part would be like this: W11 x1 plus, this is normal matrix linear algebra. So W11 x1 plus W12 x2 plus W1n xn, and similarly you will get all the other rows. And f of q would be the norm of w square, norm of q square, which is q1 square plus q2 square up to qn square. Okay, so in this particular example which I have shown, that Wnx, your q would turn out to be 0.22 and 0.26. You are multiplying a 2 cross 2 matrix with a 2 cross 1 vector, and therefore you get a 2 cross 1 vector at the output. And at this output, at the L2 output, you will get a 0.22 square plus 0.26 square, which is 0.116. This is the, up till here is the forward pass. Is this clear?
Yes.
Okay, so
Yeah.
Now when you are talking about vectors, or matrices, or more than one dimensions effectively, so always remember that the derivative that you compute would be of the same dimension as the original variable. For example, q here was 2 cross 1 dimensional, so the derivative of the function with respect to q would also be 2 cross 1 dimensional, because otherwise you won't be able to add that gradient component or subtract that gradient component from q. So this is the capital delta, so also known as nabla, I think. But anyway, the del q of f would be dou f dou q1 and dou f dou q2. These are the two components of q1 and q2. Here in this case, q is 2 dimensional, and you take a derivative of the function with respect to both of them individually. So here you would get 2 times dou f dou q1, since f of q equal to q1 square plus q2 square plus dot dot up to qn square. When you take a derivative of dou f or derivative of f, partial derivative of f with respect to q1, all you will get is 2 q1, and dou f dou q2 would become 2 q2. Okay, and these values are given, so it is just 2 times this particular value, which is 0.44 and 0.52. Till this much is clear, right? Hello?
Why we are squaring here for f?
That is the way you are defining, right? F of x equal to wx square.
Okay.
So that is so first you have written q as wx, and then you are squaring the norm of q, you are squaring.
Gradient qf is equal to,
Huh?
after that,
No, I did not get your question.
bottom second line. From the
Bottom second line. Yeah, so bottom second line. So this is the derivative of f with respect to q. Now since q is a vector, I have given this nabla sign, okay, or this big delta sign. So this big delta means I have to take the derivative of f with respect to each component of q. Q had 2 components here, q1 and q2. If you see 0.22 and 0.6, so q is a 2 dimensional vector. So I am taking the derivative of f with respect to these 2 components, dou f dou q1 and dou f dou q2, and so dou f dou q1 would be nothing but 2 times q1, correct?
Yes.
Yeah, so dou f dou q1 would be 2 times q1, and dou f dou q2 would be 2 times q2, and therefore you get this value of 0.44 and 0.52. Okay, so now you have come up to here. You need to find out the derivative with respect to w, and you need to find out the derivative with respect to x. Okay, now remember the derivative of with respect to w would be a matrix, because w is a matrix, and the derivative with respect to x would be a vector, because x is a vector. So first let me calculate the derivative of with respect to w. So for finding out the derivative of f with respect to w, we require the derivative of q with respect to w. because derivative of f with respect to q is something which we already have. We just require the derivative of q with respect to w. That is the only thing remaining. So q would be wx. So q is defined as wx. So q is defined when you define q as wx, it is w11 x1 plus w12 x2 plus w1 and x1. Now these are again considering w and x to be n dimensional vectors or n matrices. So and w21 x1 plus w22 x2. So let's consider it's a 2 cross 2 matrix, then it will be just w11 x1 plus w12 x2 and w21 x1 plus w22 x2. These are the only two values that will be there. Okay, so now let me ask you one question. What would be the value of dou q1 dou w11? Can somebody answer that? Dou q1 with respect to dou w11. x1, correct. Okay, what would be the derivative of dou q2 with respect to w11?
0.
Yeah, it would be 0. So these points are clear, right? I mean, you can see it from, you can denote the first row as q1, the second row as q2 and so on. So dou q1 by dou w11 would precisely mean that, okay, I am operating in the first row and I am taking the derivative with respect to w11. There is only one term which is there, which is w11 x1, and therefore the derivative of this would be x1. Similarly, dou q2 by dou w11, which is the second row and the derivative with respect to w11, there are no terms which depends on w11 in the second row, and hence that would be 0. These 2 points are clear, right, with everybody?
Yes,
okay.
yes, clear.
Yes.
Yeah, okay. So therefore we can write this in a fancy fashion like dou qk, which is the kth row, and the derivative with respect to wij, which is the ijth element of the matrix W. We can write it as, so first thing is, if you see dou q1 into dou w11, it would be x1. If you take dou q1 with respect to w12, it would be x2. So dou qk by dou wij is precisely equal to xj. However, it will be xj only when k equal to I. So this is something, this 1 which you see, 1 with a subscript of k equal to I, this means that it is a indicator variable. This will turn 1 only when k equal to I, otherwise it will be 0. So when k equal to I, we will have the value as xj, else it will always be 0. Is it okay, this notation?
Yes, yes,
okay.
yes.
Okay, so going forward, now we can break it up into many parts. Like we need to have dou f by dou wij, which you first, since you have dou f dou k individually, so you take dou f dou qk and dou qk by dou wij. You do them for all k's, that is for all the rows of k, all the rows of q. And you again, so dou f dou qk, you already found out that to be 2 qk, and this qk by dou wij is the thing that I just told, which is the indicator variable into xj. So this you get from here, the first term 2 qk, and the second term you get this. Now this term of the second term 1 k, the indicator variable of k equal to I and xj, this will only turn 1 when k equal to I, and therefore in all of these k summations there will be only one summation which will hold when k equal to I, and therefore this value becomes 2 qi into xj. Is this clear? Hello?
We are listening.
Yeah, this is not clear, is it?
No, sir, as such it is clear. The only thing is we need to know about all these things.
See, you understood how this the indicator variable came, right?
Yeah, that's right.
Now and you understood how this 2 qk came.
Yeah.
So
yes.
Yeah, so this summation is clear to you. Now in this summations there will be, in this summation there will be k terms, which will be 2q1 into the same thing, again 2q2 into something. There will be k such terms, and only in one of those terms can k become equal to I. So for that particular k only that sum will be there, all other terms will turn to 0 because one k equal to I will become 0 in that case.
Yeah.
Okay, so yeah, so this, I mean, this will require a little bit of linear algebra maybe, and this is precisely the reason why I did not show the entire backpropagation algorithm, because that uses this extensively. Okay, this particular thing is used extensively in backpropagation. So okay, so I will not go into the details of this, but you can just take it from me that this 2qi into xj, this can be written in a matrix form or a vector form as 2q into x transpose. So I have given you two examples here, that dou f by dou w12 is actually, if you go by this equation, that dou f dou w12 is nothing but 2q1 into x2, which is coming from this equation. Again the underlined equation, it is 2q1 into x2, and dou f dou w21 is 2q2 into x1. So if you do this q into x transpose, you will get these values. So just take it from me. I know that linear algebra is something which is a roadblock here, but this is the way backpropagation is calculated for matrices. And similarly you will find a similar thing for dou f dou x. I am not going into the details of this because again I know that this might be a bit difficult, so I am skipping these points. So finally coming to neural networks. So this up till here, these two particular things, the vector notations and the matrix notation is something that you would need to understand in order to understand the backpropagation algorithm in neural networks. But if you understand these 2 points, how dou q, how dou f, dou w and dou f, dou x was computed, you would understand the backpropagation algorithm from the first point till the last. I have given you all the ingredients of it, but you need to understand these two things you will need to understand. Okay.
Yeah, sir. For us, like we need to understand that how backpropagation works. Now, if it is like including matrices or the vectors, we need to learn linear algebra, right?
Correct,
if it is
correct,
yes. And y thing, we could understand it easily. Now, if it is turning into bigger vector.
Now, see the matrices that I showed you here is like 2 cross 2, and anyway the matrices that I have showed you here are very small. Normally in today's deep learning research or work, all the matrices will be of, let's say, million dimensions. Okay. God. So you will need to understand linear algebra before you can go into the actual, because otherwise I could have shown you the backpropagation algorithm, it will be just gibberish to you all. So I just showed this because the previous examples I showed in order to make you understand how this computational graph helps. And finally, if you just know the rules of linear algebra, then you can do the same thing in modern deep learning also. That is the crux of backpropagation.
But in fact, sir, see, we should know the concept which you have just told us.
You should always know the concept. That's true. But I would suggest you to go through the basics of not the basics of linear algebra. What I hope you will get hold of these lectures. What I have shown. So, for example, you try to do this particular example by yourself, and when you get stuck, you can look at the notes. You will get some feel about how this entire thing is working.
Sure,
okay,
sir. We'll
so that will help you get an idea about how this. This is just a toy example with a 2 cross 2 weight matrix and a 2 cross 1 vector. So this will help you in the long run. Okay, so that is the main point that I wanted to make today. But because since neural networks is the lecture content for this week. Okay, so this is one such neural network. I've drawn it very badly, but it's like you have some inputs, you will have some hidden layers. So these are the hidden layers, the two hidden layers. These are the two hidden layers, and this is the output. This is supposed, this can be called by multiple names, like this can be called to be a 2 hidden network, 2 hidden layer neural network, or a 3 layer neural network. You can call it as you wish. When the number of hidden layers goes beyond 1, we call it deep neural network. Okay, and that is the basic building block of deep learning today. So all the nodes are connected to all the nodes in such a neural network. I have not drawn all of them, but all of these nodes are connected to all of these nodes in the next layer, and so these are known as the fully connected layers. All nodes have some associated nonlinearities, and these nonlinearities are called the activation functions. And where does backpropagation play a role in this case? For example, if you see the output layers, suppose you are doing a 4-class classification, and so at the output layer you will have some cross entropy loss, and from that cross entropy loss you will, and the things that you will update are these edges that you see. All these edges are basically weights. So these weights are something that you will update based on your loss function. So you will try to update the weights in the same way as I have told. So for example, this is your x and this is your w, so you will do the same thing here, and you will update w in such a way that your loss goes on decreasing. Okay, that is the way backpropagation comes into the picture. And yeah, so activation functions. So I wanted to give you a brief overview of why different activation functions are required. So don't think about this ReLU activation function right now. Just think about the sigmoid activation function. So sigmoid activation function is given by 1 by 1 plus e to the power minus x, and this is the graph of the sigmoid activation function. Okay. So if you take x and if you take a sigma x of that or a sigmoid of that, you will get a y. So as I said, by the chain rule, dou L of dou x equal to dou L by dou y into dou y of dou x. And dou L by dou y, as I said, the sigmoid function has a derivative of sigma x into 1 minus sigma x. So this is the derivative. This point is clear, right, to everybody? Why dou L dou x becomes this?
Yes, yes.
Now think about two possible conditions. Think about this region and think about this region. What will happen when x is such that the sigma x value comes here, comes in this on the right hand side, or the right hand side mark where I have put? What happens when sigma x comes to this particular comes in this region? What will be the value of dou L dou x?
One.
Dou L dou x will be something in terms of dou L dou y. So let's remove dou L dou y now. Just consider sigma x into 1 minus sigma x. What is the value of sigma x in this region?
1. A constant.
It is 1.
Or 1.
No, it is 1.
1.
So if it is 1, then what is this value? Sigma x into 1 minus sigma x?
0. Next
So,
is 0.
so what is the value of dou L dou x?
0.
So,
0.
so if you're, so this is one of the major problems in sigmoid activation. Like if your x becomes slightly positive, then dou L dou x becomes close to 0, which means that your network stops learning, because your gradient was flowing till y, but from x onwards it becomes 0, because dou L dou x is 0. So everything else, everything to the left of x will also see a 0 gradient, and there will be nothing there. Is this point clear?
Okay.
Yes.
And the similar thing will happen when x becomes negative.
Okay.
Because x becomes negative means sigma x becomes 0. Sigma x becomes 0, and if sigma x becomes 0, then again dou L dou x will turn out to be 0. So there will be no gradient. So even if x becomes highly positive, or not even highly positive, if x becomes moderately positive or moderately negative, your network will fail to learn, because there will be no gradient. If there is no gradient, your network won't be able to reduce the loss function at all, and therefore it will fail to learn.
You mean to say that sigmoid is not useful in this case?
In this case, in most cases, sigmoid is never used in the as activation functions of neurons in the middle layers. In the final layer you can use, because sigmoid has some good properties there, but so sigmoid is generally, for example, sigmoid will never be used in the hidden layers of a neural network, because hidden layers is something where you want to learn. Sigmoid will be used in the output of the, sigmoid may sometimes be used in the output of the neural networks, because there you
only when it is a binary classification problem.
Only if it is a binary classification problem. Even in a binary classification problem, you may not use sigmoid. You can use two nodes at the output and assign one node to 1 and assign the other node to 0.
Single node will also do.
Single node will also do, but the learning might be, the learning in that case might be a bit, what should I say, it might not converge easily because of the sigmoid activation function. Okay, so it's always a better idea to use two nodes even for binary classification, assigning one node for one class and 0 and the other node for the other class. Okay.
What are the advantages?
The advantage is you are not using sigmoid, so not using sigmoid is a big advantage, and and it has been seen that the training of the neural network in such cases is much more stable.
So model is not learning in that case.
Model will learn in sigmoid, but the learning may not be stable. So stable means your model may go up to your loss might suddenly become nan, or something might happen. You won't understand what is happening, but it's some problems might creep in your so that is an issue that sometimes appears with sigmoid functions, but people still use them. But I and most other papers that I have seen recently, they generally use two, even for two class classification or binary classification, they will in most cases use two nodes at the output. Okay.
Recommending sigmoid in the last phase only.
Recommending sigmoid in the last. Sigmoid should never be used in the hidden layers. That is for
possible. Okay.
That is for certain. Sigmoid should never be used in the hidden layers. Can be used in the output layers, but still people don't use it that much. Okay.
How about softmax as compared to softmax?
Softmax is used much more. This thing. I mean, softmax. The usage of softmax is much more common, because in a multi-class classification you will always use softmax.
Is useful in hidden layers also?
No, softmax is also never used in hidden layers. In hidden layers, the main activation function that is used is this ReLU. Okay. Now, so as I showed in sigmoid, there were saturation on both sides, on the positive side as well as the negative side. ReLU solves it on the positive side. ReLU makes it max of 0, x. So any x that you have will again receive a 0 gradient, but any x that you have positive in the positive, you will always receive a gradient, because y equal to x in the positive direction. Okay. So dy dx will always be equal to 1, dou y dx will always be equal to 1. So whatever y will change, the same thing x will change accordingly. So that is the advantage of ReLU over sigmoid. However, ReLU has the same problem, like there is a 0 gradient on the negative side. So ReLU has the same problem in the negative direction, and therefore ReLU has been modified slightly, saying that okay, ReLU has the same problem, therefore leaky ReLU, which is, it is a max of 0.01 x and x, which is this side will be x, but this side will be this side will have a slope of 0.01. So there will be slight gradient that is coming from the negative side, but a 1 gradient which is coming from the positive side. Okay, so I will, it's gone till 5:45 now, so I will quickly go through some questions, and so then I'll close the session for today. So the first question is training a neural network, we notice that the loss does not increase in the first few starting epochs. What is the reason for this? So what is the reason? Can somebody say? Learning rate is low, regularization parameter is high, stuck at the local minima, all of this could be the reason.
Stuck at the local minima.
Okay, and stuck at the local minima is obviously correct. Learning rate is low, is that
And
Yes,
what
it
is
is right.
regularization parameter?
Regularization parameter is okay. I have not told regularization parameter. Regularization parameter is sometimes what you do is you take a 2 norm of your weight matrices. You don't want your weight matrices to grow very large in 2 norm. In the normed sense, you don't want your matrices to go up very high values. So therefore, what you do is you do mod of lambda square and mod of w square and take a lambda with that, and you add that to the loss, which means that if your w becomes very high, then your loss will also become very high, and therefore your network will try to keep your w to low values. So that is the regularization parameter in this case would be lambda. Okay, this is the definition of regularization parameter. You add lambda norm of w whole square. That lambda is the regularization parameter. Okay, so what is the reason for this? If your learning rate is low, then can your model not in training a neural network, we notice that the loss does not increase. Actually, it should be decrease. But anyway, I mean, this is the question that was given in the last year's assignment. Anyway, okay, so consider when can your network not learn? One is it can be stuck at the local minima. If your learning rate is low, will that affect your network learning?
Of course, sir.
Yeah. Yes.
Okay, so A is correct, C is correct.
All of above could be reason.
Could be the reason, but why is B correct? See, if B is correct, I mean B is obviously correct, but why is it correct? I told, what did I say? The regularization parameter is lambda into norm of w whole square. So if your lambda is very high, so let's say your lambda is infinity, let's say, just consider your lambda is infinity, then even a small non-zero w will increase the loss to infinity. Am I correct?
Yes.
So your network won't allow that, because loss being infinity is something that it doesn't like. It tries to reduce the loss. So your loss will kept at 0, and with lambda equal to lambda being a very high value, the only way you can keep a loss to a very minimum value is if you don't increase w from 0 at all. You keep w 0 also. Then your loss will also be 0, and it's good. Loss, the minimum value of loss that you can anyway have is 0 in this case. Therefore, if your regularization parameter is very high, then your w won't change from 0 or the initialization point, and therefore that could also be a reason that your network is not learning. Okay, is it fine?
All of the above, no?
All of this above could be the is actual answer.
Okay.
Okay, then going on to question 2, what is the sequence of the following tasks in a perceptron? Perceptron means maybe you just talk about neural networks. So the first point is initialize the weights of the perceptron randomly, go to the next batch of the dataset. If the prediction does not match the output, change the weights for a sample input, compute and output. What should be the sequence of tasks that you do while training a neural network?
It is D.
It is D. Okay. Does everybody agree to that, or does somebody have some other answers?
D only.
It's D only. Okay, then I think this question is fine. I'll go on to the last question, which is, which of the following is true about model capacity, where model capacity means the ability of the neural network to approximate complex functions. As the number of hidden layers increase, model capacity increases. As dropout ratio increases, model capacity increases. As learning rate increases, model capacity increases, and none of these. Which one?
A.
Yes, the other two, B and C, they are both hyperparameters, and therefore they don't, model capacity doesn't change on depending on whether you change your hyperparameters or not, and therefore A is the correct answer. Okay, I hope I could make some sense about yeah. So one thing is, I'm sorry that I couldn't go through the matrix part, but linear algebra is something that you would need to understand in order to understand backpropagation completely. And so okay, so any other, so it's been a long lecture today. Thank you, sorry for extending it by so much, but yeah, if you don't have any more questions, I'll close the call.
Actually, we should thank you.
Yeah.
That's
Right.
fine, that's
It's
fine.
not some sense, it's lot of sense. We learned a lot. Today we learned a lot.
Okay, good to know that. So okay, so I'll close the call now. Thank you.
Thank you, sir.
Thank you.
Thank you.
Thank you.
Yeah.
Thank you. Thank you.